We are going to look at limits visually, so pulling the value of limits off of a graph. So let's just look at this first one. The limit as x approaches -1 from the left-hand side. So here's our graph. Here's -1. Okay, if we're going to approach x equals -1 from the left-hand side, we're going to see what's happening to our output as we approach that x value. So as we approach -1 from the left-hand side, we're approaching 3. Right? So we say the limit is equal to 3. So now let's do it from the right-hand side. Again, here's -1. Here's our graph. We're going to approach input -1 and see what happens to our output. As we approach that input, it seems like we're approaching an output of like 0.8. We can just approximate there and say it's about 0.8. Let's keep going. So remember this notation, limit as x approaches -2, right? Well, that means we're going to approach from both sides. So we're going to approach -2 from the left and from the right and see what we're approaching. In this case, we're approaching the same thing. It seems like we're approaching 1. So we can say the limit as x approaches -2 is equal to 1. Okay, but then what if I say the limit as x approaches -1? Okay, well, we already figured out that from one side we're approaching 3, from the other side we're approaching like 0.8. So since we're approaching different things, do the limit does not exist dance, we can say this does not exist. Okay, D, N, E. Alright, so let's keep going. F of -2. Alright, so this is an important distinction to make. So the limit as x approaches -2 is equal to 1, as we already talked about, right? But the second that we actually hit -2, the graph jumps up here, and that's the point, right? So there's a hole at -2. That's what we're approaching as x approaches -2, right? But then at -2, f of x is equal to 3. So we say f of -2 is equal to 3. All right, another quick distinction. Usually with a piecewise graph like this, where there's breaks in the function, one of these holes will be filled in. So we'll say like this one's filled in. So in that case, we would say f of -1 is equal to 0.8. Okay, the limit from the right, 0.8. The limit from the left, 3. And then f of -1 is equal to 0.8 because that's where the filled in point is. Okay. Limit as x approaches 1. Okay, so let's look at x equals 1. Let's see what happens to our outputs. As x approaches 1 from the right, we're going to infinity. As x approaches 1 from the left, we're going to infinity. So what we're going to say is our limit is quote-unquote equal to infinity. All that means is that our output is going to get bigger and bigger without bound. Obviously, infinity is not an actual number, so we can't technically say equals infinity. But what this means is that we're going to just approach infinity as we get closer and closer to that input. So then what's f of 1? Well, f of 1's undefined, right? Because it's infinity. So it's a vertical asymptote. We're not defined. Our function is not defined at f of 1 or at x equals 1. So 1 is not in our domain. So we cannot say f of 1 is equal to anything. Let's see. The last thing I want to do is talk about the limit as x approaches 2. So the limit as x approaches 2 of f of x. So what we notice is as we approach the input 2, the output seems to be approaching 1. So we'll say that the limit's equal to 1. Now, yeah, this isn't an asymptote. It's not a hole. It's not a piecewise break. But we can still define limits at every single point on this graph. We just typically only talk about limits when there's like a piecewise break, when there's a hole, when there's a vertical asymptote, because that's when they're most interesting. But technically, we can take a limit of any x value in the domain of this function. All right, so that's it. You should be able to do the next few questions of the Desmos activity.